I don't have to do any introduction. Thank you very much. Good evening, everybody. I'm Stefano, and I'm a postdoc here at Leiden Observatory. And as Caitlin said, I work on stars and exoplanets, and in particular on the stellar magnetism and how it affects the environment in which exoplanets are. But tonight I'm going to talk about magnetic fields of stars specifically and how they change over time. So that's why we're going to kind of tie that to dancing and rhythm. Maybe, maybe not. Aha! Was it me or was it the? Was it you? Oh, no, okay, it was me. Okay. So, stellar magnetic fields. This is a picture of the sun, and we've overimposed the complexity of its magnetic field. I'm going to talk about it a little bit more in detail later, but we already see a lot of things going on. We have things on small scales, and we have large scales structures going on. Now, I'm an observer, and when I see something like this, I'm excited and it's beautiful because there are a lot of things going on, and I'm curious about each and every one, what they are and how they're going to evolve. But when you are when you are a modeler, you don't really like this, in the sense that figuring out a way to put in equations and in theory exactly what is going on here, it's a mess. It's really, really complicated, to the point that even for the sun, which is the most studied star, we do not have a complete theory that can explain all of these phenomena. So I'm going to talk about the theory, just like a brief mention. In order to generate magnetic fields on stars, we need two main ingredients. We need convection, which is shown here on the left. It's basically bubbles of plasma that are seething on the surface. They start as literally hot bubbles in the interior of stars, and then they rise to the surface, they cool down, and then they go back inside in a cyclical fashion. It's pretty much what we do when we have to boil water for pasta, hopefully. And then we also need rotation. The star, they spin they spin, and in particular, the sun on average spins every 27 days, which means that 1 day on the sun is equivalent to 27 days on Earth. And when we have these two ingredients, we have a charged fluid that is undergoing convection and rotation at the same time. We have something called dynamo. And that is what generates and sustains the magnetic field of stars throughout their lifetime. So this is the theory in a nutshell, which is, of course, really simple in these terms. It can explain a lot of stuff, as I was saying, but not everything. Now, let's go back to this picture 1 second. As I was saying, we can start to decompose this picture in different ways to understand more what we are seeing here. We have small-scale structures on the stellar surface, like spots, which are dark regions over here, and also brighter regions, which are called faculae. Now, these dark regions, the sunspots or star spots, are dark because the magnetic field is so intense that it can actually divert the flow of light. So light would not pass through there, it would find other ways to come out of the star, and that's why they're dark. This is on the small scale. And then what we have is large scales as well. And in the jargon, what we say is that the large-scale magnetic field of the sun is a dipole. It's basically a big magnet with northern and southern polarity, or positive and negative polarity, depending on how you see it. But it's basically a massive dipole, a massive magnet. And so we have on the large scale here coming out of the star. Now, people have been observing the sun for a long time. This actually cuts to the beginning of the previous century, but people have started to observe the sun in an astronomical way, of course, not just looking at it, way before that. And what they've seen is that they counted the number of spots on the surface, and what they've seen is that it varies over time. The number of spots oscillates. It goes from a minimum, where the star is basically almost immaculate, and then it goes up to a certain number of spots, which, as we can see, it also varies over time. And this is called solar cycle. It lasts 11 years. And we go, as I said, from a state where the star is relatively quiet, it doesn't have many spots, to a state where it has a lot of things going on, a lot of energetic events, magnetic events, and so on. And then it goes back to be relatively inactive. And this is on a time scale, as I said, of 11 years. This is on the small scale, because we're talking about spots. But then there is also the large-scale magnetic field. And that one varies over 22 years, so double as much. So, we start from a configuration that is like this. It's a big dipole. Then, 11 years after, the dipole flips the polarity. The poles become, where it was northern, it becomes southern, and vice versa. And then, 11 years later, again, it becomes like the initial configuration. So the magnetic cycle sometimes is referred to as 22 years, because we restore the same configuration at the beginning. And in the meantime, it's undergoing all of that I was saying before. So all the mess that is going on at the small scales. Now, the sun has rhythm in that sense. It's capable of sustaining a magnetic field throughout its lifetime. It is 11 years long, or 22 years long. And we sort of can explain that, more or less. So the question now becomes, what about the other stars? Do they have magnetic cycles? And if yes, how? And that's very important to study, because with that we can test the robustness of our theory. If our theory predicts something, and then we go out there and we say, oh, it should be like this, and it's not, then maybe our theory is not that good. So we need this kind of feedback between the other stars and the solar dynamo theory itself. So, other stars. This diagram basically encapsulates the types of stars, the various types of stars, but also at different stages of their life. This is called HR diagram, or Hertzsprung-Russell diagram, which were basically the first astronomers who used this. And it's very useful because it puts the luminosity of the star, of the object, against its temperature. So we have bright objects and hot objects over here. Hot is blue. We also have different stages of the life of the stars. We have young ones, we have middle ages, and we have older stars, and those that are even kind of leftovers of dead stars. But what we're going to focus here is the main sequence, which is this diagonal here, and that is where the stars spend most of their life. In particular, my work focuses on solar-like stars. We have here the sun in yellow, and what we're called red dwarfs, or red stars, which are colder and also dimmer. So we are in this part of the graph, pretty much. Stars are point sources, as we say in kind of technical terms, because we don't have something called spatial resolution. We're not able to distinguish features singular features on the surface. If anybody can tell me what is going on this one, from where you are, congratulations, I cannot even from here. And this is not even a point, so there are some pixels here, but it would be, a star would be literally a point. So we lose this information on the spatial scales, on the small spatial scales of the star, and therefore what we cannot do is to count spots on other stars. So we have to come up with other methods that are called indirect, because we cannot directly see the evolution of the surface of the stars. There are many ways to sort of apply these indirect methods, but I'm not going to talk about them here. I'm just going to focus on one in particular, which is what I do, which is called spectropolarimetry. It's kind of a mouthful word, so I'm going to kind of try to break it down. Spectra means that we need to record the colors of light and how intense they are, which is this part over here. And polarimetry, polarim, is basically it records how light vibrates in different directions. So what we want to do is to study how intense and how the direction in which colors vibrate at the same time. So that's why we kind of compress everything into one word. We could use only this part to study magnetic fields, sure, but it will only give limited information. It will not give us information about the configuration of the magnetic field, its geometry, its orientation. That's why we need this polarimetric part, because this is the part that is sensitive to the large-scale magnetic field. So, okay, I'm going to be a bit more technical here. What we use is a specific technique called Zeeman Doppler imaging. It's similar to tomographic imaging and also MRI, sort of, kind of thing, like from medicine. What we have here is a time series of spectropolarimetric observations for which we have a specific signature, and if we have that signature, it means that we detected a magnetic field. Great. Detecting a magnetic field is awesome, but then what we have to do is to monitor the magnetic field. And by monitoring, I mean we have to cadence the observations as the star rotates, so that we see how this signature evolves over the stellar rotation. By doing that, we would have something that changes over time. This is basically, you can imagine this GIF by being these ones kind of stuck together and made as a GIF. This is time that it is going on. And we have this polarimetric signature that changes over time. Because of this change, we are able to build a map of the magnetic field, and kind of on the large scale, and tell more or less how it is, how it looks like. So what we want to do is to reconstruct a map of the magnetic field at a certain year, then come back to the star a year later, redo the same process, and see if the magnetic field has changed somehow. And then again and again and again. I mean, if you get the observations, of course. So, at this point, I wanted to show a few results of my research. And in particular, I'm going to focus on 3 active stars. Active means that they have very strong magnetic fields, 1,000 times stronger than the Sun. So these are monsters compared to the Sun. And these are red dwarfs. So those that were in the diagonal, they were kind of dim and cold, so to speak. So this is AD Leonis, which is, yes, a star in the constellation of Leo. And as we see here, these are different reconstructions of the magnetic field. We have the negative polarity in blue and the positive polarity in red. And this one is basically, on the left there, is basically a dipole, like the Sun is on the large scale. We have its 2 polarities and so this big magnet. As we can see, over time, this dipole is tilting more and more, and it's kind of pointing towards the equator. Eventually, the star could go on and flip its polarity. So it might have a cycle, a magnetic cycle, that would look like the solar cycle. So this would be a first result. And this is very important because we have never seen this kind of cycles for stars that are this cold, so to speak. Now, we have another star in the constellation of Leo, and in this case, as you can see, the dipole is not really caring much. It's just sitting there chilling and being always symmetric with respect to the spin of the star. So this star seems to not have a magnetic cycle, or maybe because our observations span from the beginning of 2019 to the beginning of 2022, maybe our observation window was too short, and therefore we're not grasping the real, maybe it's a very long cycle, it's not 22 years, maybe it's 50, and therefore this is not grasping that variation. And finally, we have another star, EV-LAC, and this one, it had already a tilted magnetic field, and it goes even further. It actually reaches the equator in this case. And so as the previous one, it could also go further and eventually have a polarity reversal, polarity switch. So, this is basically my last slide, and the takeaway message is that stars are very dynamic, especially in terms of their magnetic field. They can host magnetic cycles, especially also the red stars kind of have rhythm in that sense, and also other kind of stars have rhythm. And they may have the same rhythm as the sun, they can kind of dance the same song, but they can also dance more exotic songs or doing something different. Or eventually they might as well not, because some of them are not really showing evolution. So with that, I'm going to stop here and I'll take questions. Thank you.
Questions for Stefano in the back?
Yes. Yeah, so thank you so much for this presentation. I'm a biologist myself. This is quite far from my field, so this is really interesting to see this type of research as well. So in your presentation you showed us that there's no spatial information about these stars because you can observe the spots on them. But for mapping the magnetic fields, you need to have some sort of information about the rotation of these stars. How do you know how fast it rotates?
So, by the way, exactly, I would refer to the next talk. Yes, the short answer is basically that we use other techniques. Okay, you can imagine that, for instance, when a star has a spot on it, let's say just one, as the star rotates, the spot rotates. So the amount of light that you receive will vary over the course of the rotation of the star. When the spot is out of view, then you will receive the maximum amount of light, and when the star comes into view, it decreases. So you will have like a fluctuation in time of light, of the brightness of the star, and that is a way, for instance, to infer rotation periods.
Thank you.
Yeah. Why do you focus on dwarf stars, red dwarfs?
Okay, that's a good question. Because my supervisor told me to? No.
Yeah, I do that.
But, so, this is a mess. Magnetic field-wise, this is, forget it. So for young stars, we can apply the same techniques I showed tonight for stars that are not even here, that are even younger than this. So they're kind of arriving on this sequence. We can apply the same stars. I'm not doing that because I can just not do all types of stars, basically. So that would be the answer. But then we have other stars, and the problem is that for these kind of stars, from the sun down, we sort of can explain them with the theory about the sun. But then when we go up here, the interior of the star changes. We don't really have convection anymore, so we need something different to explain the magnetic fields. And then giants and supergiants, it's very long in time, and as Victor will say, when old stars, kind of the magnetic field is so low that we can even barely detect it, so it would be quite difficult to do that at the same time. Yes?
Yeah. Sorry, I'll defer to you.
Okay, let's go there.
Yeah, what instruments do you use? Is it space-based telescope? I imagine you need a spectrometer and polarizing thing in front.
I
on Earth.
wish it was a space-based instrument. I really wish it was, but no, it's a ground-based telescope. It's so a couple of them are in Hawaii, one is in France, and the other one is in Chile. And in order to do this, doing this in space, it's really hard because the stability and the temperature of the instrument must be really low, and the sun is really hot in space, let's say. So yes, it's ground-based. In particular, the instrument I'm using is called Spirou, with French accent. It's it's the spectropolarimeter in near infrared. So we use near infrared, kind of here, like this kind of stuff, but here, and then we also use optical, so visible light. Yeah.
You said that you observe it the spots by the dimming of the star.
Yep.
But then how do you separate it from a planet dimming the star?
Very good. We cry a lot. It's all about modeling, and I mean, if usually the time scale itself and repetition of the same event helps. If you have a planet that is exactly like at the same time of a spot, I'm so sorry, we cannot do much about it. But at a certain point, they would lose coherency in the sense that one would have a lag with respect to the other, and that would help. But you need repetition. You need a lot of observations in that case. That's why these kind of stars that we assume they're really spotted are particularly difficult because they introduce a lot of signals that we could mistake for planets. Was it from there? Yeah.
Over the course of the lifetime of the star, is the cycle consistent or does it change? Like,
it's a good question. We do not really know because we don't have many. So we have been observed as much, even though we haven't been observing the sun for 300 years. That's not enough, and we don't have and we have observations for other stars, for cycles of other stars, but it's not enough. What we need to do is to kind of take different stars at different ages and see what they have, if they have.
and is there a correlation, for example, as older the star is longer the cycle, or as younger the star is shorter?
I'm looking at Victor. No, in terms of age, it would really, it's hard to say. We don't have enough data to speak about correlations or statistics. Yeah, behind?
Thank you for your presentation. And as I understood, I'm not sure you have a pattern for magnetic field of the stars. For example, red dwarf and the sun and blue ones even. So we have a pattern. Is it limited or unlimited patterns? And you refer to determinism or not?
Oh, I'm used to people shouting at me. So the last part was if we are seeing patterns across the different types of stars.
Yes.
And the second part was determinism? No? I mean, I know the word determinism, but what do you mean in this context?
I mean, do you think there is a kind of mathematical sequence for magnetic field of the star or not?
Okay, I forgot the first question. Okay, patterns. Let me answer that first. In terms of cycle, again, no, we don't have enough data to talk about patterns and talk about what we can see. What we have, it's messy because here, like for instance, if we look at these stars with the same properties have completely different magnetic fields. So why? So for instance, is that because the magnetic fields are intrinsically different? Or is it just because these stars are having two different cycles going on and I'm taking a snapshot for one and I'm taking a snapshot for another one and I'm just simply saying differences? We still don't know. We need more observations for that. And as we go up here, up here, up here, it's even worse because maybe we have 3 or 4 stars that we can actually detect magnetic fields that are really hot. So talking about cycles for those, we kind of stop here. And we have other stars for which we have solar cycles, like they look like the sun, yes, around here, but going up, it's tough. And the determinism, sure. In the sense that, what was the question? I forgot. The determinism as in like, what was that?
Mathematical model.
Oh, mathematical model. Oh, to explain that, no, because we still have nothing to explain. Because we still don't know. That's what I mean.
Okay, so I think that's our last question. So let's thank Stefano again. We're now going to take a break for about 10 minutes and then reconvene to start our quiz games. So please take 10 minutes to go get drinks or what have you.